My name is Emma Gardner and I'm a Research Fellow on the Landscape Decisions programme based at the UK Centre for Ecology and Hydrology. I'm leading a project on modelling the landscape level benefits and biodiversity consequences of woodland creation. Working with a range of stakeholders, together we'll try to answer the key question, how many trees should we plant and where? My research background spans several disciplines. I spent 5 years working in astrophysics, building detailed computer models to understand the drivers of variability in complex interacting systems. Since moving to ecology, I've worked on woodland fragmentation and carbon fluxes. I've worked with NGOs to derive species abundance indices from citizen science data. And my most recent work at the University of Reading has involved working alongside ecologists, economists, and social scientists to model the impacts of land management on ecosystem services within agricultural systems. In this project, I'll be combining these different elements to help examine the benefits and consequences of woodland creation in agricultural and peri-urban landscapes in the UK. The UK government has pledged to increase tree planting to 30,000 hectares per year by 2025, and many community groups are already embarking on local tree planting initiatives. Woodland creation can bring many benefits, including carbon sequestration, flood alleviation, recreation, reduced air and noise pollution, and shelter belts for crops. However, woodland creation also has big consequences for biodiversity, and these are not always positive. While woodland species may benefit from increased habitat and increased connectivity, open habitat species may face reduced habitat, loss of connectivity, and even increased predation if new woodlands are created on areas of open habitat that they depend on. This means we need tools to help us identify the best locations for new woodlands so that we can maximise benefits to people while still balancing the needs of other species. These tools must couple ecosystem service models to biodiversity models, something which is rarely done, and these biodiversity models must realistically reflect the way species with different habitat requirements move around the landscape. This is something that is not possible with most current metrics. Most biodiversity metrics, such as those currently used for net gain calculations, are score-based. This severely limits their ability to capture biodiversity impacts. Habitats typically receive a good to bad condition score, but this overlooks the fact that good condition for one species may be bad condition for another. Conversion from one good habitat, such as grassland, into another good habitat, such as woodland, may theoretically produce no change in the metric. Yet this hides, in reality, a complete change in underlying species composition, as species that did exist in the first habitat simply cannot exist in the other habitat no matter how good it is, because it doesn't provide the conditions they need. As well as a condition score, habitats may also receive a connectivity score based on proximity to other natural habitats. But this single score neglects the fact that some species can travel further than others. It also often neglects permeability of intervening habitats and the fact that permeability is again species dependent. Some bird species may have no trouble flying across a motorway, but the same land use would be impossible for an amphibian. On top of this, some species require a mosaic of habitats in close proximity that serve different requirements. If we are to create successful nature recovery networks, we must better understand and assess connectivity. This means bridging the gap between the simple connectivity metrics used in practice and state-of-the-art connectivity modelling. But unlike existing models such as Rainshifter, we mustn't just focus on the connectivity needed for individuals to disperse through the landscape to populate other areas. If we want to support biodiversity in a given area, we must make sure we capture the habitat connectivity species need for day-to-day foraging and survival, because we know the optimum configuration for this is often different to the optimum configuration for dispersal. For this project, I will build a new biodiversity model designed to simultaneously and realistically capture the habitat and connectivity requirements of multiple species. I'll link this to ecosystem service models that quantify the key benefits of woodland creation for people. Then I'll apply the combined model to quantify the benefits and trade-offs of woodland creation in agricultural landscapes. The biodiversity model will output abundance and connectivity metrics for 6 species groups of conservation concern, specifically chosen because they require connectivity at different spatial scales and represent different responses to woodland creation. The model will do this by explicitly simulating their daily foraging behaviour. To account for their different foraging strategies, the model will include an existing central place forager submodel, which I've already validated for bumblebees, and a least cost forager submodel. This will be a new hybrid model built specifically for this project. It will blend traditional least cost and agent-based modelling techniques from ecology with the latest gravity modelling approaches from astrophysics. The model will be co-developed alongside NGOs to ensure it incorporates the most up-to-date understanding of species ecology and validated against the latest citizen science datasets to ensure it reproduces observed species abundances. The biodiversity model will then be linked to ecosystem benefit models from other landscape decisions projects. Incorporating the Invest Water Yield model, which has already been validated for the UK, and a carbon sequestration model currently being developed by the Agland project, will allow the combined model to capture the two key benefits landowners most often seek from woodland creation. We know that the tree nesting bumblebee is spreading across the UK and becoming an important crop pollinator, so we will also include a crop pollination service model, since the project focuses on woodland creation in agricultural landscapes. The combined model will then be used to test woodland creation scenarios. We know that the landscape level benefits and biodiversity consequences of woodland creation not only depend on where the woodland is placed in the landscape, but also on properties such as the size and shape of the woodland and the type of trees. Working with stakeholders, we'll identify study areas, define and simulate realistic woodland creation scenarios, and then use the combined model to quantify the benefits and consequences of these new woodlands. This will generate spatially explicit woodland creation recommendations for specific study areas of interest to project stakeholders. From these specific case study areas, I'll then use mathematical techniques to derive general woodland creation guidelines that can be applied more widely. I'll categorize subregions within the study areas using the farm archetypes developed by the Agland project. I'll then analyze the simulation results for each subregion using mathematical methods more commonly used in the physical sciences to identify how landscape types and configurations resonate with species movement properties and ecosystem benefit provision. This will allow me to identify the most beneficial scenarios for each farm or landscape type, and so create overarching general guidelines, i.e. if your farm or landscape is like this, then this is likely to be the most beneficial woodland creation scenario. The project will produce three key outputs overall. Firstly, spatially explicit woodland creation recommendations for specific study areas of interest to project stakeholders. Secondly, overarching general woodland creation guidelines, which will be co-produced in accessible formats alongside stakeholders and a written communications expert. Finally, the combined model itself will be converted into a freely accessible online model tool for project stakeholders to continue to use after the project finishes. This project will combine ecosystem benefit models from existing landscape decisions projects with a new biodiversity model co-developed with NGOs. Guided by project stakeholder needs, the combined model will be used alongside expertise from the physical sciences to try and answer the question, how many trees should we plant and where? The project will generate both specific and general woodland creation recommendations that account not only for human-centric benefits, but also realistically incorporate the complex and often conflicting needs of other species.